So let's talk about how you might go about designing a heuristic that is admissible. Remember that the heuristics that we're trying to make are an estimate of the cost of the shortest path from a given node to the goal. And it should be relatively inexpensive to compute, but help us to make better guesses about where we're headed. And so for every node in our state space, right, every state in our state space, right, we need to have a value, if this is, node 1, node 2, node 3, node 4, node 5. We have to have a value for the heuristic at 1, heuristic at 2, and so on. And, maybe 5 is our goal, and we're trying to get an estimate of the cost of the shortest path to the goal. So h of 1 is the shortest path to the goal from location 1. And h of 2 is the smallest, the estimate of the shortest path to the goal from location 2, and so on. And remember, the special thing about an admissible heuristic is that it's non-negative and it is less than or equal to the actual path cost, right? So we're trying to make it an estimate of the cost of the shortest path to the goal. And now we have to guarantee, if we want to say it's admissible, we have to guarantee that it's going to be less than or equal to the actual cost of that path. Now, why do we want an admissible heuristic? Well, A star, if you use a heuristic function h, is always true if we have to start by saying that h has to be an admissible heuristic, okay? So we get our optimal solution if all the following are true. One of them is that h has to be an optimal heuristic. Another is that there is some solution, of course. And then we have just like the extras. The branching factor has to be finite, right? You can't have an infinite number of neighbors for each node or each state. And all the arc costs are greater than some value that's greater than 0, right? So we don't have increasingly smaller and smaller arc costs. So let's go back to an old problem that we had before. We have this robot delivery problem where the robot needs to start in room C, pick up the package, and then deliver it to room A. So over here, I have a picture of my state space, right? And we have, initially, the robot is in room C without the package. That's what the X means. And the connections between the rooms are, well, if the robot's in room C without the package, it could move to B without the package. It could move to A without the package, and back and forth. We can also pick up the package, which it looks like has a cost of 1/2. And then once we have the package, let's just pretend we can't. Well, I guess no, we can put the package down in this thing. But once we have the package, we are trying to get that package to our goal, to room A. And the I'll say goal of the problem or whatever, but the optimal solution is one that is the shortest path from the start state to the goal state. So in this particular problem, it's one heck of a simple problem, right? I mean, the shortest path is going to be 1/2 plus 1.5, 2.5, right? The shortest problem is going to be 2.5 units, right? The cost is going to be 2.5. And we could have a more expensive solution to this problem. Like I could say, start here, right? Don't pick up the package yet. Instead, go to room B, then go back to C, then go back to B, then go back to C, then go and pick up the package, then go to B, then go to A. Not exactly ideal, right? But it's a legitimate path. It's just not as good as the shortest path. Okay, now remember that a heuristic is an estimate of the cost to get to the goal, right? For this particular problem, it's pretty darn easy to figure out the actual costs, right? But we're trying to develop a heuristic, but just to talk about what are the actual costs so that the heuristics that we come up with, we can be sure that they are in fact admissible. I just want to know what are the actual costs to get to the goal. So for example, and there should be a start arrow here. Sorry that there's no start arrow. But if I start here, the cost from here to get to the goal is 1/2 plus 1 plus 1. And I could, in fact, compute the cost to the goal for each of these things, right? If I'm already here, shouldn't get there, but if I am here, the additional cost to the goal would be 1, 2.5, 3.5, 4.5, right? So here is my graph where I've told you what the actual costs are to get to the goal from each state. And I guess I should say the actual minimal cost to get to the goal, because of course if we start at C without having the package in our hand, we could say C to B to C to B to C. So we could go like 1, 2, 3, 4, 4.5, 5.5, 6.5. But I'm looking for the actual smallest cost to get to the goal. And again, I'm trying to find these numbers because I'm going to talk with you about designing an admissible heuristic, and I want to make sure that our heuristics are admissible, and we know that they're admissible if the value of the heuristic is less than or equal to this number. Now, again, I'm just going to say it one more time. This is a really, really small graph. Since it's a small graph, we can look at it. We don't need heuristics, okay? We don't need to come up with a heuristic for this graph. We're going to do it anyway because it's a useful exercise, and I want to talk to you about some ways to think about how you could come up with a heuristic for a different graph that you might have. So if this were actually a graph with, 10,000 nodes and they weren't just aligned in a line, but they actually, each state had lots of different connections, it would be harder to come up with the actual costs of these nodes. Yeah? And there are some very specific rules in this problem. You can only pick up the package in room C. The cost to move between the rooms varies. Well, in this one it doesn't. It's actually just 1. But we've put a number on each of these transition states, right? So we could say that the cost is different to get between A and B or B and C or whatever. But this is our actual graph with the actual costs written on it. Normally we might have the actual graph, right? We would be able to construct the actual graph 100%. We know it. That's part of a state space problem. But we wouldn't actually know these costs, right? The blue costs here, okay? And we know the rules for the big problem. A problem with fewer restrictions on the actions is called a relaxed problem. And a graph of the relaxed problem is a super graph of the original. So in other words, we have this graph, and what I'm going to do to relax the problem is I'm going to add some arrows between some of the states and say that that's going to help me figure out maybe some cheaper costs. Just like we sort of often will use as a heuristic for a map, the distance as the crow flies, right? Because we know that as the crow flies is the shortest distance between 2 points, and so it's got to be an admissible heuristic. And it's usually something we can measure pretty quickly, even if we don't know all the details of the road that we're on. Okay, so suppose that I change the problem slightly. I'm going to relax the problem, and I'm going to say, you know what? It's not just in room C that you can pick up the package, right? But you could pick up the package anywhere. Yeah? You can pick up the package anywhere. I'm just going to make that rule, okay? So that means that I'm going to actually add an arrow so you can pick up the package there. Or I guess you can put it down. Might as well let you do that too. And that costs 0.5. Or we let you do it here, okay? This is not a real rule for the problem. However, if I happen to know something about the problem, I know the distances between the rooms, and I just pretend like I could do it anywhere, right? Then if I happen to be in room A, I could estimate how much it would cost me to get to room. If I'm in room A without the package, I could estimate how much it would cost me to get to room A with the package. I'd just say, oh, that's just 0.5. It's not the actual cost, but it is less than the actual cost. So this would be formally my actual heuristic, right? If I have the package, then the heuristic is just the distance to the room. And if I don't have the package, the heuristic is the distance to the room plus a half. And I'm going to apologize that I don't have all those arrows in here, but you know that the actual problem starts with, oh dear, I didn't want to erase that, starts with C as the, C without the package as the start state, because of course we have to well define our problem. But remember that even if we start with this as our start state, We still need a value for the heuristic for all the other states that we might not even visit. So here's my updated, here's my sort of heuristic that's pick up the package anywhere, okay? Pick up the package anywhere. The heuristic for the state where you are at state A and you don't actually have the package already, you can solve the problem in just half a step, right? That's going to be my heuristic, the value that is indeed less than or equal to the actual cost, right? Because I just added some arrows. Why not? Yeah. And I've come up with each of these blue numbers, right, based on this rule for my heuristic. So now I have the actual costs on there. Of course, in the real problem, we wouldn't know those. But we might know the distances between the rooms, and we probably know how much it costs to pick something up. We just might not know, maybe that's the distance between the room as the crow flies, and it just so happens that right now our rooms are set up beautifully like this. Let's add another arrow here, and we'll add an arrow there just to show you that that is in fact the start state. But the idea here is that's the actual cost. Here's one set of heuristics that I could use, right? The blue numbers here. And is it an admissible heuristic? Absolutely, because every single number here is less than the actual smallest cost to get to the goal. All right. Here's another example of an admissible heuristic that I could do, which is I'm going to say, what I want you to do is get yourself to the package, pick it up, and then make it to the goal. So with a cost of 0 for that movement. So for example, if I were at state C and I have the package, then I can teleport to A for a cost of 0. And if I'm at state B and I have the package, I can teleport to state A at a cost of 0. So here's formally how I would do that. I would say if we have the package, then the value of the heuristic is 0. You just are at the goal. And if you don't have the package, then the heuristic value for that state is going to be distance to the package plus 0.5. And so here you go. I'll draw that arrow in again. Remember that arrow should be on all of these, right? The start arrow, oops. And it should be in there, and it should be in there. Cool. But our question is, do we have the package? If we do, the heuristic is 0. If we don't, the heuristic is the distance to the package plus 0.5. So now, that's my heuristic, 0, 0, 0. If I have the package, that's the heuristic. And if I don't have the package, then the cost is how much does it cost me to get there plus 0.5. That's how I did the heuristic, right? Okay. And it's effectively, coming up with that heuristic is effectively adding some arrows to the graph that I already have, right? And remember again, I don't actually, in the real world with a big problem, I don't know the cost of every, I don't know the actual costs, but I have some way to cheaply estimate stuff, like cheaply estimate how much it costs me to get between rooms, say. So here's an interesting question. What if I made my heuristic figure out the maximum of these guys' of the numbers for each of these, and put it as the heuristic for this value? And I should note, by the way, that this teleport to the goal thing, right, that we had as our second option, this is an admissible heuristic too, because if I look, 2.5 less than or equal to 4.5, 1.5 less than or equal to 3.5. 0.5 less than or equal to 2.5, and so on, and 0, well, that's equal to 0, but that's okay. Yeah? Okay, so the question is this heuristic still admissible if I take the maximum of the other two? Because remember, as we said, you can always make the heuristic 0, the value of the heuristic 0 for every single state, but then it doesn't help you very much. If you think about A star, if the heuristic is 0, then that's just lowest cost first search, because we're just back to using the path cost so far. So let's see, that would make the heuristic for this guy 2.5, And the heuristic for the next one, because I'm just looking at the maximum of this and this, it makes it 1.5, and so on. And here's what I eventually end up getting, right? 2.5, 1.5, 2.5, 2, 1, 0, because I took the biggest. So 2 versus 0, I'll take the 2. And 2.5 versus 0.5, I'll take the 2.5, and so on, right? And is this still admissible? Well, of course it's still admissible, because when I said I could pick up the package anywhere, I said this was an admissible heuristic, which means for each of these states, the actual cost, well, the heuristic value was less than or equal to the actual cost. And here, the heuristic value is less than or equal to the actual cost. So if I just, all the heuristic values of the states are less than or equal to the actual cost. So look at that. I come up with another combined heuristic that is admissible, that's actually looking pretty good. So thinking about relaxing a problem is one way to come up with a stronger heuristic.